So when electron configuration of ion. Okay, yeah. So we can do, when we do ionization, I'll do that right now. Just ionization in general. So this is the Saturday morning study session. This is for just the part of the intro to the recording. So we're going to go over cation and anion formation. And then we'll make a connection to electron configuration as well. So in general, when you are talking about an atom, you're just going to assume it's neutral. So let's take the nitrogen atom and just look at some qualities of the nitrogen atom. The nitrogen atom has 7 protons and 7 electrons if it's neutral, if they're the same. And sometimes I'll just think of protons, the proton count as a positive number and the electron count as a negative number. So it's like a +7 and a -7. If we combine these, we'll get 0, and that's neutral. So anytime you have an uneven number of protons and electrons, that's when you have an ion. So let's say we have a atom of nitrogen, and it now has 10 electrons. Well, I'll treat those 10 electrons as a cumulative -10, and we can just combine these to get the charge. Now, we would write that N with a -3 on top. Anions are, anion is just a name for a negative ion. Anion is negative. So anion is just a term. And cation is just the term for positive ion. So when we look at the periodic table and we're trying to figure out some patterns from the periodic table, there's some areas of the periodic table, some elements that consistently go through cation formation, and there's some elements that consistently go through anion formation. So I can show you which ones those are. Let me pull up the periodic table. Now, before I jump to the periodic table, to do a quick example of the electron configuration part of that, when we are comparing neutral nitrogen, and sometimes you'll have nitrogen with a 0 on it versus nitrogen with a -3 charge. We'll talk about why I'm choosing -3 specifically. Neutral nitrogen with its 7 electrons. Anything with 7 electrons is going to have this configuration: 1s2, 2s2, 2p3. And that's just the ground state, that's the predicted state that the first 7 electrons are going to assume. And when you ionize, in this case, to a -3 charge, that's gaining of 3 electrons. And so we're going to add 3 electrons to where they would predictably go, and that's going to fill up the outer shell. The idea is the ionization is predictable when you know how many are needed to fill up the outer valence shell. So with nitrogen's case, there's 3 empty spots in its p orbital. So it's going to predictably gain 3 electrons, so it has its full outer energy level. Once this is full, it has what's called a noble gas electron configuration. So it has the same electrons as a noble gas would in its neutral state, and this is stable. So that is the goal of ionization, is to fill up the outer shell. So in terms of predictability, we just look how many empty spots are there. There's 1, 2, 3 empty spots. So we know that nitrogen in particular would always ionize by gaining 3 electrons under natural conditions, under normal conditions. And if I were to do another example, like with a metal, where we have something like potassium. Well, potassium only has 1 valence electron, and if we look at its electron configuration, it has, what was it, argon? Argon, and then 4s1. So it just has 1 electron in its outer valence shell. And so metals as opposed to nitrogen and the nonmetals. Metals are going to lose its valence electron because it only has one. And when it loses one electron, that's cation formation. So it essentially is going to have the same electron configuration as argon. I'm kind of cheating because normally that's not how you do the electron configuration of argon. And one of the homework questions had that. You do the previous noble gas and show that whole shell. So still, again, with the ionization, the goal is to have the same number of electrons as a noble gas. And that's where K would go to K+. So if I asked for the electron configuration of ionized potassium, it would be the same electron configuration of as argon, which in this case, if I did the correct way, it would be neon 3s2 3p6. So that would be the electron configuration of ionized potassium versus the electron configuration of neutral potassium. And I'll jump to the periodic table in a second. If you have questions on this initial part, let me know. I had a quick question about photoelectron spectroscopy. If you have your peaks, and just assume that they're separating between first energy level, second energy level, third energy level, with S, P, 3S, 3P just going in order. And the question is, how do isotopes affect PES? Well, the isotopes, the only difference between isotopes is a different number of neutrons. Which is going to affect the mass number. So assuming that this right here has a value of 4, this would be neon 3s2 3p4. And we can look at this element and figure out what element this is. This could be sulfur. So what are some possible isotopes of sulfur? Well, if we look it up, we see that the average for sulfur, if we look up on the periodic table, it says at 32.07, which is a average mass. So we can assume that there's some isotopes smaller, some isotopes larger. So it could have sulfur 32, let's say sulfur 33, and 34 just for kicks. Let's say these are possible isotopes of sulfur, where the vast majority of sulfur is going to be sulfur 32, since the average is really close to that. The only difference between this is neutrons. And my question back to you, I guess, would be what is affecting the electron distance from the nucleus? What would cause the electrons to be closer to the nucleus or further from the nucleus? And does that have anything to do with neutrons? If it does, then yeah, we could talk about the shift. If it doesn't, then I would say no change to your question. Yeah, see the protons, that would be the nuclear charge for the protons. So if we take a look at sulfur and look at the predictable ionization of sulfur, what kind of ion will sulfur form? And I'll talk about, I got another question about d orbitals. I'll talk about the ionization for d orbital elements. It's a little trickier. So sulfur predictably ionizes to a -2 charge. And so it's going to have the same electron configuration as argon when it ionizes. So it has that full third energy level of electrons. And we could see that this 3p peak can go up and match the 2p peak when it ionizes. Now, that's not the only change. What else would happen? I guess to answer your question, why I think about that is the isotopes would not affect your peak left or right or height or anything like that. Isotopes wouldn't affect this. But charges do. Would you expect these to shift to the right or the left if we have high binding energy on the left and low binding energy on the right? So when the atoms get smaller, more energy to be removed caused by particles getting closer together. And this is Coulomb's law. The idea that the closer the charged particles are to each other, the stronger their attractive forces are felt. So more energy to be removed would be caused by them getting closer together. When sulfur ionizes, does it get larger, or does the atom get larger or smaller? There you go. Yeah. So in this case, the initial question becomes, is the atom larger or smaller? And we can often go back and reference what's happened to the atom. Is it larger or smaller than its original state? And then we can use that to justify the rest of our claims. So if it's larger, it's not more energy to be removed. It's actually, each one would be less energy overall. Because now all the electrons are drifting a little bit further from the nucleus. So we would assume that all of these would shift a little bit to the right as a result of anion formation. And if you want to have some sort of thing written down just to remember the trend, anions will shift it to the right, cations will shift it to the left, assuming that it's arranged high energy on the left. I think that'll help. So less energy to be removed as caused by particles now being further away from each other. Increased distance between particles. So this, I'm trying to like use these arrows to show like a flow chart of justifications because one concept leads to another. So hopefully that's a little bit clear from my mess of a drawing right here. But you get two options. Does it get larger or smaller? Okay, as a result, are those particles closer together now or further from each other? And if they are, we can say that it's, in this case, because they're further away from each other, each of the electrons now should cost a little bit less energy to be removed. Now, this is mainly addressing the first ionization, the first electron to be removed. Once we pluck off the first electron, then it changes the atom again. Once you remove an electron, then it's going to get smaller again. And then remove the second electron, it's going to get smaller again. So this is, right, what we did right now is just preparation for that first electron to be removed. So hopefully that helps. Let's do an element with d electrons and the valence shell for that. And we can go back and ask a question about this if we still have a question. So on one of the questions that I had you do in your group work was talk about gallium and which of do the electron configuration for gallium. And so 1s2, 2s2, 2p6. Right now we're at neon, 3s2, 3p6. I like to sometimes think about the landmarks along the way as far as the noble gases. And I know that after this, we have gallium, which will be 4s2, 3d10, 4p, and then 1. Every once in a while, if you look at textbooks, every once in a while they rearrange this last part. And they may actually just put the d orbitals first. They might say 3d10, then 4s2, 4p1. It represents the same thing, but the idea that after argon, there's gallium still has 13 electrons after argon, and whether the d orbital is written in the middle or first doesn't particularly matter. I like the top one because this is the order in which they fill and it helps keep it straight in my head. But the second representation shows specifically which electrons are on the outer energy level. So these are valence electrons because only valence electrons are only on the highest energy level. And then the d electrons, yeah, they filled up after the 4s orbital, but the 3d electrons are still in the third energy level. So those aren't valence electrons. In terms of gallium, gallium has 3 valence electrons. And when they lose these 3 electrons to ionization, we can say that gallium is in that same group as aluminum. So it predictably is going to have a +3 charge when those leave. And so, yeah, ionization for elements with d orbitals is still focused on just s and p electrons leaving. There are some weird exceptions that pop up, but we don't really need to know the exceptions for that. Like copper has a weird configuration. Why does iron have a +2 state or a +3 state? I can kind of show that really quick. That might help. Let me talk about iron really quick. So we haven't memorized this yet, but iron and other transition metals have more than one type of ionization possibility. So iron can form a +2 ion or a +3 ion. Chromium can do the same thing. And we're going to start memorizing these after this unit. And then copper, for example, could be a +1 or a +2 state. And so different transition metals can ionize multiple ways. And that's why we can't really use the periodic table to predict the ionization. We have to look at compound formations. And I mean, vanadium can have like 3 different, it'd be like +2, +3, +5. And so just to give an example of why this happens, for iron, if we look at its last energy level past argon, so we have argon, and then we have 4s, 3d. It's a little bit easier to see when we do the orbital diagram. Here's iron, and so it has those 6 electrons in the d orbital. Now, if it ionizes, it's not really going to lose just 1 electron. It could lose 2. And where do those 2 come from? So to get to this +2 state, we can say these 2 electrons leave. And the result that happens is the electrons actually do some fun little rearranging. So if these 2 electrons leave, it's normally an empty shell for 4s. And what happens is the atom will stabilize itself, and what it'll do is actually move one of these electrons to spread out. If there's a little bit of a gap in the orbitals after ionizations, the electrons will, and for transition metals, will often like rearrange by 1 just to have half-filled orbitals. So this electron actually will leave the d orbital and jump to the s orbital. And now what do we have? We have an ionized state of iron where the s orbital and the d orbital are all half-filled, which is a little bit more stable configuration. So when the entire block is half-filled, you're maximizing the positive spin states, which is the more quantum mechanical way to approach it. But there's stability in half-filled orbitals. And that's the quantum mechanical way to describe stability is electrons are stable and the positive spin state, which is the up state, is maximized. So in this case, that's what a +2 configuration actually looks like, and just showing kind of where these electrons would jump around. If I draw in blue, the one that jumped over to kind of fill the gaps of what was lost. And then iron +3, that extra ionization, because this happens in stages, where would that electron leave from the 4s? Would that next electron be a 4s electron or a 3d electron that's taken away? What would leave? What do you guys think? So because the 3d fills up after the 4s, it is a higher state for the electron to be in, a higher energy state for the electron to fill that. We're not necessarily distance from the nucleus, but the order in which they're filling. So the atom prefers to have stability in the 3d orbital versus the 4s orbital, just because the 3d orbital is a higher energy state for the electron. And when I say higher energy state, that's not necessarily distance. So for iron +3, we see that this is a stable ionization for iron because that last 4s electron can leave, and what's remaining is a half-filled 3d orbital, which is still has an increase in stability. And I could do this for copper as well. Chromium kind of does the same thing. Manganese is a little tricky. Manganese, chromium actually has an irregular configuration at the beginning. To show you one of the irregular ones, because people are asking about that. When you look up electron configurations of transition metals, and I can actually show you, this is pretty cool. Let me show you something you can do on ptable.com if you're curious. When you go to energy levels, let's see, does it do the, if you go to energy levels on here, it shows you the electrons, and I'm trying to think of, it should show you there we go. At the top, you can switch to electrons, and then it'll show you the orbital diagram right here in the middle. So as you fill up potassium, you can see right here in the middle that I'm looking at is potassium, then calcium, you can see the 4s filling up. Then you go scandium, there's a 3d electron in the middle, titanium, vanadium. These are all assuming ground states. Now look at the difference between vanadium and chromium. It goes from 3 electrons in the d orbital to all 5. That extra electron came from the s orbital. Look at the s orbital. For vanadium, it has 2 in the 4s orbital. Then with chromium, one of these leaves and half fills 3d orbital. So chromium is irregular because it is half-filled 3d orbital and half-filled 4s orbital, instead of 2 in the s and 4 in the d orbital. And copper does the same thing. You can see cobalt, them filling up as normal, as expected, and then with copper, instead of having the next one here in the 3d orbital going down, it spreads out and takes another one from the 4s orbital. So 4s is half filled and completely fills the 3d orbital. So copper and chromium are irregular. Now you don't have to remember that for the AP test, which ones are irregular. Just know that if you see this and an example is presented to you and shown like why does this happen, it's because there's stability in full-filled orbital blocks and half-filled orbital blocks. And this largely happens with transition metals in their d orbital, little tricks to half fill and completely fill. Silver does the same thing. If we look at silver, 1 in the 5s orbital and a completely filled 4d orbital. Gold does the same thing. So copper, silver, gold all do this little trick where borrows an electron to half fill or to completely fill that d orbital. Whereas here's, yeah, you can just click on, like if you're curious about some of these, even the f orbital stuff, the reason why f orbital is a little weird is because even though lanthanum's down here, notice how lanthanum's in this lower orbital we call the F block, but it's electrons in a D block. And then if I jump over one, then it starts filling the F block, one in each. And then when you get to PR, there's no more d orbitals and there's just 3 in the f orbital. It gets a little weird when you get to f orbitals, so we don't really have a go through and predict f orbitals, like 1 d orbital and then the d orbital's gone. It goes back over to the f orbital, so it gets a little weird once you get the f block. So just predicting from scratch what the electron configuration is of f orbital stuff is a little tricky, so we don't do it. But predicting d orbital stuff is very doable. Like chromium, you can see one half filled, half filled. Molybdenum does the same thing, half filled, half filled. Yeah. So that's this weird thing that happens with half filled orbitals, just to make sure that if you have s and d orbitals half filled, it's a little bit more stable than just 4 in the d orbital. Does that kind of help a little bit, or that just overly confuse you guys? So with the periodic table, just to briefly review, this zigzag line that starts here and goes down here, this separates the metals from the nonmetals. So everything on the left of this, except hydrogen, is going to be, so I'll just do a little outline. Everything here are metals. These are metals. And then I'm going to not bubble in the metalloids. Take them off. Bye. I'll see you later. And then these are nonmetals. So one of the big properties that differentiates metals from nonmetals is how they ionize. So what we can predict is that metals will be, when they ionize naturally, is they're going to form cations. So metals consistently lose electrons when they ionize. And that's one of the main properties of metals and the main thing that differentiates metals from nonmetals. And so when nonmetals ionize, they form cations or anions, and they gain electrons. Now, what we'll get into when we do chemical bonding and do the approach of when we talk about salts and ionic compounds is we'll get into a little bit more about why they lose electrons and gain electrons when they ionize. But right now, just knowing that this is the trend is going to help us. As far as which ones we can predict group 1 and 2 elements, and 3, this block on the first 2 groups and the last 6 groups, these are called the main group elements or representative elements. Or main group elements, because these are the ones that we can predict their ionization just by looking at their location on the periodic table. And this is where we say group 1 has 1 valence electron, group 2 has 2 valence electrons, 13 has 3, 4, 5, 6. This is how many electrons are in their outer energy level. And then the transition metals we kind of ignored in terms of valence electrons and ionization in the beginning. And then we can say that predictably, group 1 elements are going to have a +1 charge and a +2 charge. Hydrogen still, when it ionizes, can get a +1 charge, but there are situations where it can get a -1 charge. So usually with the group 1 metals, we start with lithium and just hydrogen as the 1 valence electron. That's why it's in that spot. 13 elements have a +3 charge when they ionize because they're still metals. Boron, the +3 group usually just starts with aluminum in terms of its ionization. In terms of its +3, gallium is a +3 like we just saw. Boron, we don't see ionize a whole lot. It's going to kind of covalently bond, so we're going to kind of ignore boron. And then with carbon and silicon, they covalently bond as well, so we're not really going to see them ionize. But then with group 5, these get the -3, -2, -1 charges predictably. because nitrogen is 1, 2, 3 away from the noble gas that it's trying to mimic with its ionization. Oxygen is 2 away, and fluorine is 1 away, as far as the electrons it needs to gain to mimic a electron configuration of a noble gas. So that's the using valence electrons in the periodic table to predict ionization for the representative elements, the main group elements. So hopefully that was useful at least, but hopefully that cleared up some of that stuff as well. Predicting based on just certain factors. For example, so these equations, even though we're not going to be calculating with them, it still may help us understand. That's not the right equation. That should be a C. Sorry, I was mixing the E equals MC squared in my head. So if wavelength increases, so you have a wave and then you increase the wavelength, what happens to the frequency? Well, as a result, an increase in wavelength is going to have a lowering or a decrease in frequency. You also should be able to look at a wave and identify what is the wavelength. You just pick it out from a visual, or look at a wave and say, how many cycles are shown here? Well, there are 1, 2, 3 cycles. So you should be able to look at a drawing and identify how many cycles are shown. So those kind of things about waves, the basics, the fundamental waves, I can ask a question about. But as far as calculations go, I'm going to go a different direction. I'm not going to have you do calculations. You do need to understand the inverse relationship between wavelengths and frequencies. If one value goes up, the other goes down, because when they multiply, their product has to equal this constant that is the speed of light, which is 3 times 10 to the 8 meters per second in a vacuum. So because they have to multiply to equal this constant, if one value goes up, the other has to go down. And that's an inverse relationship. The other thing with waves that you will have to do, let me know if you have questions along the way. The other thing you have to do with waves is apply them to the photoelectric effect and the hydrogen transition. The idea that you have a piece of metal and a wave of a specific frequency or energy comes in, and there's a minimum energy required to get this electron to leave. This electron needs to absorb a minimum amount of energy. That has to get into ionization, by the way. There's another way to talk about ionization of electrons for metals. It's essentially the same thing. The photoelectric effect is what's the minimum amount of energy to get an electron to leave a metal, which is essentially a description of ionization. And then minimum energy required to completely remove an electron. And then, so just, this could be a multiple choice question where the photoelectric effect is being described, and the description of minimum energy required to completely remove an electron is an answer choice, or you need to understand that concept to answer it. What's more likely and more common on the AP test is having to do with hydrogen transitions. Hydrogen electron transitions. And what's important about the hydrogen ion is that it only has 1 electron. So when we're analyzing the jumps between these energy levels, it's only based on 1 proton, 1 electron. And this is how we came up with the idea of energy levels, because this electron would jump very specific jumps called quantum leaps, and it wouldn't exist anywhere in between. It would just be in one spot and the other, and it released specific packets of energy. So an electron transitions to an excited state. This is the ground state, and this is an excited state. These are excited states. When an electron moves away from the nucleus, it requires energy or needs to absorb energy from some sort of source, like UV radiation or something like that. When electron absorbs a very specific amount of energy, it moves away from the nucleus, which another way to say it is moves to higher energy state or energy level. So we can see that as our first example with the arrow A. That's where it moves to a high energy state. Now, if we're moving from a higher energy state back to a lower energy state, it's not going to absorb energy, it's going to emit energy. And this is what we would see as visible light, as far as, or some sort of UV spectra or infrared spectra. When the electron moves closer to the nucleus, that electron is getting to a more stable position, and so that extra energy is being released in form of photons or some other form. The transition between a 3 to a 5 should be equal and opposite from a 5 to a 3. A 3 to a 5 should equal the negative of a 5 to a 3 in terms of energy cost. One is being absorbed and the other is being released, but they should be equal and opposite in terms of energy required for that transition to occur. And that's largely how waves are incorporated into chemistry, is with absorbing and emitting these waves for electrons to jump around the atom, higher energy states and lower energy states. So just understanding that concept, specifically of when are they absorbed and when are they emitted, is important. The other thing about this is, in terms of these energy states, when we draw on a diagram like this, what I'm writing on the side, these are principal energy levels. And so again, this 2 is broken into 2s and 2p when we do the more quantum mechanical look, when we do the orbital diagram. So right now what I'm writing are principal energy levels, the main energy level, 2, 3, 4, 5, and they get closer together at higher energy levels. So the distance between 1 and 2 is the greatest distance from the nucleus, or the largest energy jump. And they get progressively closer and closer together at higher energy levels. So what does that mean? Here's a question for you. Would you predict a 4 to a 2 or a 5 to a 3? Which one would you predict to have a higher energy wave emitted? Which transition should emit a higher energy wave? A 4 to a 2 or a 5 to a 3? Yeah. I'm going to turn on chat so you guys can type to everyone if you want. Or you can still just have to type to me. So yeah, 4 to a 2. Even though it's, yeah, exactly. Even though they're both jumping 2 energy levels, a 4 to a 2 should be a larger energy gap, just because a 5 to a 3 is closer together than a 4 to a 2. Just this general idea that as you get further and further away, the energy gap is closer together the further from the nucleus. So to a 3 to a 1, emits more energy than a 4 to a 2, and so on. Those are some other questions, just general knowledge about energy states and distance from nucleus in regards to the hydrogen atom example. Generally visible light, this might show up on the AP test, and I talked about this, but generally visible light is only transitions that go from a higher energy state and goes to the second energy level. So a 3 to a 2 could be red light, a 4 to a 2 could be green light, and a 5 to a 2 could be those blues and violets. And once we get up to the 6, this is the visible light that we see with our eyes, is some end state going to a 2. Anything past that, if you drop into a 1, any end state going to the ground state is a higher energy level, which would be UV. So you should know which transition for hydrogen specifically are visible, and that's anything from a higher level to down to a 2. And then down to a 1 would be UV, higher energy. And these are called emission series. Okay. What I'd like to do for you is be able to go through the progress check and talk about why some of these have particular answers, because these are really good questions to go over. You got the graphs, that will probably look familiar. So these are a good review of the mass questions. So if you haven't gone through this yet, these are going to be good review of the mass questions that are part of Unit 1 that we haven't done in a little bit. So I was going to go through and talk about how to do some of these, especially from the multiple choice format. So in interest of time, I might go and just record myself talking about these, and I can post that later if you haven't had a chance to look at it. But these have all the answers, and I was going to post this as a resource. The version online has an explanation for why each answer is correct that is selected. So that is a little bit more detailed. And then also the free response questions. I started looking at some of your answers for the free response questions, and particularly I was able to glance at some of Ian's. And so what I can do, and maybe Ian, I'll ask you this later, is if I can go through and grade someone's progress check free response and practice going through and showing you how I grade it. And I just record that and post that for everyone.